May 14, 1874. The Mississippi River at St. Louis, a massive steel arch bridge, stretches 520 feet across the most dangerous waterway in America. 14 fully loaded locomotives crawl simultaneously onto the span, 420 tons of concentrated weight that should collapse any structure according to European engineering calculations. Below, 500,000 spectators hold their breath. London-trained engineers had declared steel spans over 500 feet mathematically impossible. Carnegie's proven wrought iron methods dominated American bridge building. Every expert agreed that James Eads, a self-taught salvage diver with no bridge experience, was attempting engineering suicide with his untested chrome steel design. Yet as those 14 locomotives cross together, the bridge doesn't even shudder. What made Eads' 1874 chrome steel so impossibly strong that it still stands unchanged today, while modern galvanized beams require replacement every 75 years? The answer lies in one obsessive decision that nearly bankrupted the entire project. The year 1867 marked a turning point for American commerce, and nowhere was this more evident than in the bustling river port of St. Louis. The city's merchants watched with growing alarm as cargo tonnage shifted north to Chicago, where railroad networks promised faster, more reliable transport than the unpredictable Mississippi River steamboats. St. Louis faced an existential crisis: either span the Mississippi with a railroad bridge or surrender its position as the gateway to the American West forever. The engineering challenge seemed insurmountable. The Mississippi at St. Louis presented a 520-foot wide death trap for bridge builders. The river's current raced at 12.5 feet per second, fast enough to destroy any construction scaffolding. Federal navigation requirements demanded 50 feet of clearance above high water, forcing any bridge to soar higher than most buildings. The required span strength of 3,000 pounds per foot exceeded anything ever attempted in American engineering. European expertise offered little hope. London-trained engineers, drawing on decades of bridge construction across the Thames and Rhine, declared steel spans exceeding 500 feet mathematically impossible. Their calculations, refined through generations of European engineering education, predicted catastrophic failure under such unprecedented loads. Carbon steel, they insisted, lacked the tensile strength for spans approaching 600 feet. Even if the materials could theoretically support the weight, the thermal expansion and contraction across such distances would tear any structure apart within months. Andrew Carnegie's Keystone Bridge Company dominated American steel construction, and Carnegie himself preferred proven wrought iron methods. His furnaces produced reliable, tested materials that had built dozens of successful railroad bridges across Pennsylvania and Ohio. Carnegie's approach emphasized standardized production and proven techniques, methods that had made him wealthy and established American steel as a credible alternative to European imports. He viewed experimental alloys and untested construction methods as dangerous gambles that could bankrupt both builders and clients. Into this landscape of established expertise and conservative engineering stepped James Buchanan Eads, a man whose credentials defied conventional wisdom. At 47 years old, Eads had built his fortune salvaging wrecked steamboats from the Mississippi's muddy bottom, diving in primitive diving bells to recover cargo and machinery from vessels claimed by the river's treacherous currents. His engineering education came not from European schools, but from 20 years of examining structural failures firsthand, understanding exactly how materials behaved under extreme stress and how construction shortcuts led to catastrophic collapses. Eads had proven his unconventional methods during the Civil War, when the Union Navy commissioned him to build 7 ironclad gunboats in just 65 days. Working from his own designs, he delivered the vessels on schedule and under budget, each one armor-plated and armed according to his precise specifications. The gunboats performed flawlessly in combat, validating Eads' belief that American engineering could exceed European standards through meticulous testing and individual component verification. For the St. Louis Bridge, Eads proposed a revolutionary design: 3 massive steel arches using an untested chromium steel alloy manufactured by the Chrome Steel Company of Brooklyn. The central arch would span 502 feet, longer than any steel structure ever attempted. Instead of traditional wrought iron, Eads specified tubular steel construction, with each arch built like barrel staves, allowing the structure to distribute loads more efficiently than solid beams. The St. Louis Democrat praised the project as the most glorious bridge and the finest engineer in the world, but Eastern engineering establishments responded with undisguised skepticism. Carnegie's engineers questioned both the untested steel alloy and Eads's tubular arch design. European trained consultants warned that thermal expansion alone would destroy such a long span within the first winter. Railroad executives worried that the experimental bridge might collapse under the weight of their locomotives, creating a disaster that would damage confidence in steel construction nationwide. The financial reality proved even more daunting than the engineering challenges. Initial cost estimates of $4 million, equivalent to roughly $280 million today, soon ballooned to over $10 million as the true complexity of the project became apparent. The Chromium Steel company demanded premium prices for their experimental alloy, and Eads' insistence on individual testing of every structural component added months of delay and millions of additional expense. Early material disasters threatened to validate the skeptics. First steel samples from Carnegie's partner foundries cracked spontaneously in the fabrication shop, revealing that standard carbon steel lacked the molecular structure necessary for Eads' tubular arch design. The brittleness that made carbon steel predictable in smaller applications became a fatal weakness when scaled to unprecedented dimensions. Traditional welding and riveting techniques proved inadequate for joining the tubular sections, requiring Eads to develop entirely new connection methods. As 1868 progressed, the project faced a crushing ultimatum. Either Eads would solve the fundamental steel problem, creating a material strong enough and reliable enough to span the Mississippi, or St. Louis would lose its commercial future to Chicago forever. The city's merchants watched cargo tonnage continue its northward migration, while Eads struggled with metallurgical challenges that no American engineer had ever confronted. The established engineering wisdom seemed vindicated. Carnegie's mass production methods had built America's railroad network using proven materials and standardized techniques. European theoretical calculations had successfully predicted the failure of experimental American approaches. The Mississippi River appeared destined to remain an unbridged barrier, protecting the steamboat industry while condemning St. Louis to commercial obsolescence. Yet Eads refused to abandon his vision of American engineering superiority built on precision testing rather than mass production standards. By 1870, Eads had made the most expensive decision in American bridge building history. He abandoned carbon steel entirely and committed his project to the Chromium Steel Company of Brooklyn's proprietary alloy. The decision defied every principle of prudent engineering, replacing proven materials with an experimental blend that existed nowhere else in American industry. Chromium Steel Company's foundries produced small batches of their specialized alloy using techniques they guarded as trade secrets, charging premium prices that threatened to bankrupt the bridge project before construction even began. Eads' obsession with material integrity drove him to implement a testing protocol unprecedented in construction history. Every single steel stave destined for the bridge arches would undergo individual failure testing, a requirement that astonished Carnegie and horrified cost-conscious investors. Where traditional bridge builders tested random samples and extrapolated results across entire shipments, Eads demanded that each component prove its individual strength before installation. The testing process required custom machinery capable of measuring steel deflections to 1/200,000th of an inch, precision equipment that had never been applied to construction materials. The Chromium Steel Company delivered 100 trial staves for destructive testing in the spring of 1870. Eads' testing machines subjected each piece to progressively increasing loads until the steel failed, documenting exactly how much stress each stave could withstand before breaking. The ultimate tensile strength requirement of 60,000 pounds per square inch exceeded anything demanded in American construction, forcing the Brooklyn foundries to refine their chromium blend through dozens of experimental batches. Carnegie watched Eads' testing obsession with growing frustration. The Keystone Bridge Company had built its reputation on efficient mass production, delivering standardized steel components that met industry specifications without expensive individual verification. Carnegie's furnaces could produce bridge materials faster and cheaper than any competitor by maintaining consistent quality across large batches, eliminating the need for time-consuming individual testing. From Carnegie's perspective, Eads was being overly picky about material specifications, adding unnecessary costs that would make American steel uncompetitive with European imports. The fundamental disagreement reflected two incompatible philosophies of American industrial development. Carnegie championed mass production efficiency, believing that standardized processes and consistent quality control could make American steel dominate world markets through superior value and reliability. His approach emphasized volume manufacturing, predictable delivery schedules, and cost structures that allowed American industry to undercut European competitors. Individual testing of components threatened this entire system by making each piece expensive and time-consuming to verify. Eads represented a revolutionary alternative, precision manufacturing where every component received individual certification before installation. His tubular arch design treated each steel stave like a critical piece of scientific equipment, numbered and documented with specific strength characteristics. This approach guaranteed zero field failures but required 18 additional months of construction time and over $2 million in testing costs, expenses that traditional contractors considered wasteful and unnecessary. The quality control revolution extended beyond individual component testing to complete documentation of the bridge's structural integrity. For the first time in American engineering history, every piece of a major construction project carried certified strength specifications, creating a paper trail that proved each stave's reliability before installation. Eads maintained detailed records showing the exact tensile strength, compression resistance, and thermal expansion characteristics of every steel component, data that allowed precise calculation of the bridge's total load capacity. Chromium Steel Company's foundries adapted their production methods to meet Eads' unprecedented requirements. The Brooklyn facility developed new furnace techniques that distributed chromium more evenly throughout the steel matrix, creating alloy characteristics that surpassed both traditional carbon steel and European alternatives. The chromium content, carefully balanced through experimental batches, gave the steel superior resistance to both tensile stress and environmental corrosion, properties that would prove crucial for the bridge's long-term durability. Testing revealed remarkable differences between chrome steel and traditional materials. Where carbon steel samples showed brittle failure patterns under extreme loads, the chrome steel maintained structural integrity even when stressed beyond normal operating limits. The chromium alloy absorbed energy more efficiently during thermal expansion and contraction, reducing the internal stresses that destroyed conventional bridges during seasonal temperature changes. Most importantly, the chrome steel demonstrated consistent performance across all 100 trial staves, proving that the Brooklyn foundries had achieved reliable mass production of their experimental alloy. The financial implications of Eads' testing protocol alarmed investors and city officials who had expected conventional construction methods and predictable costs. The bridge company's stock price reflected growing market skepticism about experimental engineering approaches that seemed to prioritize theoretical perfection over practical completion. Bank loans originally secured on $4 million cost projections faced renegotiation as testing expenses pushed total project costs toward unprecedented levels. Yet the testing program yielded one crucial result that justified every expense: zero component failures during fabrication. Traditional bridge construction typically experienced 5 to 10% material failure rates during assembly, forcing contractors to order extra steel and accept delays as defective pieces were discovered and replaced. Eads' individual testing eliminated these field surprises, creating construction schedules that proceeded without material-related interruptions. Carnegie's resistance intensified as Eads' success with chrome steel threatened the established order of American steel production. If individual component testing became the industry standard, traditional mass production advantages would disappear, forcing every steel manufacturer to invest in expensive precision equipment and time-consuming verification processes. The Keystone Bridge Company's competitive advantage lay in volume production and standardized quality, not in boutique manufacturing methods that treated each piece as a custom product. By 1871, Eads had proven that American precision manufacturing could exceed European theoretical standards through empirical testing rather than mathematical calculations. The chrome steel staves demonstrated performance characteristics that surpassed anything produced in British or German foundries, validating his belief that American engineering superiority lay not in copying European methods, but in developing revolutionary approaches to material science and quality control. The construction challenge that awaited Eads in 1871 defied every conventional approach to bridge building. Traditional methods required extensive scaffolding across the entire span, but the Mississippi's federal navigation requirements made such scaffolding impossible. River commerce could not be interrupted for the years necessary to complete construction, and the 12.5 foot per second current would destroy any temporary supports within weeks. Eads needed to build his massive arches while keeping the shipping lanes completely open, a requirement that forced him to pioneer an entirely new construction methodology. The solution emerged from studying ancient Roman construction techniques combined with cutting-edge engineering principles. Eads would build each arch outward from the stone piers using the Cantilever method, the first major application of this principle in American bridge construction. Each arch would grow simultaneously from both sides of the river, extending piece by piece into empty air until the two halves met at the center span. The method required extraordinary precision since 8 separate tubular ribs per arch had to align perfectly when they finally connected, with tolerance margins of no more than 1/16 of an inch. Construction began with wooden towers rising 120 feet above each stone pier, their timber frameworks designed to support the enormous weight of steel arches as they extended across the Mississippi. These towers functioned as construction platforms and anchor points, housing the steam-powered machinery that lifted each chrome steel stave into position. The engineering calculations required to balance cantilevered loads as the arches extended hundreds of feet from their supports, pushed American structural analysis into uncharted territory. William Chauvenet's mathematical precision proved crucial as construction progressed through 1872. His calculations determined exactly how much weight each partially completed arch could support before the cantilever principle reached its limits. Every steel stave added to the extending arches shifted the load distribution, requiring constant recalculation of stress patterns and support requirements. Chauvenet worked closely with Henry Flad to ensure that European engineering standards for load distribution were not just met, but exceeded through American empirical testing methods. The precision required for tubular rib alignment created unprecedented challenges in construction sequencing. Each of the 8 ribs per arch followed slightly different curves as they extended from the piers, requiring custom calculations for every single steel stave. The Chrome Steel Company delivered components numbered and sized according to Eads' exact specifications, but thermal expansion during hot Mississippi summers and contraction during winter months constantly altered the alignment calculations. Construction crews had to adjust for temperature-induced changes that could shift measurements by several inches across the 500-foot spans. Steam-powered construction equipment operated from the wooden towers, using block and tackle systems to position steel components with the accuracy demanded by Eads' cantilever method. Each chrome steel stave weighed several tons and had to be maneuvered into precise position while crews worked hundreds of feet above the rushing river. The installation process required coordination between multiple crews, working simultaneously on different ribs of the same arch, their activities synchronized to maintain the delicate balance that kept the cantilever section stable. Henry Flad's expertise in pneumatic caisson construction became essential as foundation work progressed beneath the river's surface. The stone piers supporting Eads' arches had to be anchored 123 feet below the Mississippi's surface, deeper than any previous American construction project. Flad's European training in compressed air techniques allowed workers to excavate and pour concrete foundations in the underwater chambers while maintaining structural integrity under enormous water pressure. The cantilever construction method attracted international attention from engineering publications that had initially dismissed American bridge building capabilities. European observers watched with growing interest as Eads' arches extended farther into open space than theoretical calculations suggested possible. The chrome steel's superior tensile strength allowed longer cantilever extensions than traditional carbon steel could support, validating Eads's decision to invest in experimental materials despite their enormous cost. By September of 1873, the Eastern Arch approached its moment of truth. 250 feet of steel extended from each pier, reaching toward the center span where the final connections would prove whether Eads's calculations and Chauvenet's mathematics could achieve the impossible. Crowds gathered along the St. Louis riverfront as construction crews prepared to install the final steel staves that would close the arch and demonstrate whether American engineering had truly surpassed European capabilities. The successful closure of the Eastern Arch on September 14th marked a triumph that reverberated throughout American engineering circles. The 502-foot span held its own weight, plus the construction equipment without deflection beyond calculated limits, proving that chrome steel and cantilever construction methods could achieve spans that European theory declared impossible. Church bells rang across St. Louis as citizens celebrated the visible proof that their city would have its railroad connection to the eastern markets. Engineering magazines worldwide published detailed analyses of Eads's achievement, praising the innovative combination of American materials, science, and construction techniques. The cantilever method eliminated the need for river-spanning scaffolding while delivering precision that exceeded traditional building approaches. European engineers grudgingly acknowledged that American empirical testing had produced results superior to their theoretical calculations, marking a fundamental shift in international engineering prestige. The success of the Eastern Arch validated every controversial decision Eads had made throughout the project. Chrome Steel Company's expensive alloy proved its worth under actual construction loads, while individual component testing eliminated the material failures that plagued conventional bridge projects. The cantilever construction method demonstrated American innovation in practical problem solving, turning the Mississippi's navigational requirements from obstacles into opportunities for engineering advancement. Yet 2 more arches remained unfinished, and the final connections would test whether Eads's revolutionary methods could be replicated consistently across the entire span. The Eastern Arch's success created expectations that the remaining construction would proceed smoothly, but the Mississippi River and the complexities of precision engineering still held surprises that would challenge even Eads's meticulous planning and revolutionary materials. The disaster that nearly destroyed Eads's reputation struck during the final arch closure attempts in May of 1874. After months of meticulous cantilever construction extending from both piers of the western span, the center tubes refused to align. Measurements revealed a catastrophic miscalculation. The final steel staves were 2.5 inches too long to fit together, creating an impossible gap that threatened to invalidate 3 years of revolutionary engineering work. The construction crews stood helplessly on their wooden platforms 120 feet above the Mississippi, staring at chrome steel components that had cost thousands of dollars and months of precision manufacturing but could not complete the arch. The mathematical precision that had made Eads famous now worked against him. Tubular construction demanded exact alignment that traditional solid beam bridges could accommodate through minor adjustments, but his innovative stave design offered no margin for error. St. Louis newspapers, which had celebrated the Eastern Arch's success 8 months earlier, turned viciously against the project. The St. Louis Republican published scathing editorials declaring Eads's entire approach fundamentally flawed and calling the incomplete bridge Eads folly, a monument to American engineering arrogance. Eastern engineering publications seized the opportunity to vindicate European skepticism, publishing detailed analyses explaining how American empirical methods had failed, where European theoretical calculations would have prevented such costly mistakes. The financial consequences proved even more devastating than the engineering humiliation. Bridge company stock crashed as investors fled a project that appeared doomed to remain forever incomplete. The 2.5-inch gap became a symbol of American industrial overreach, proof that experimental materials and untested construction methods could not replace the proven techniques that had built European infrastructure for centuries. Major banks that had financed the project faced potential collapse as their bridge-related loans appeared worthless. Carnegie and the Keystone Bridge Company watched the crisis with grim satisfaction. The failure validated everything de Carnegie had argued about Eads's perfectionist approach. Individual component testing and experimental materials created expensive complications that mass production methods avoided. Traditional wrought iron construction would have allowed field adjustments to accommodate minor measurement errors, but Eads's chrome steel tubular design demanded precision that proved impossible to achieve in actual construction conditions. The steamboat lobby, which had fought bridge construction for decades, launched a coordinated campaign to capitalize on Eads's difficulties. River transport interests argued that the incomplete bridge proved railroad crossings were inherently unsafe, pointing to the engineering failure as evidence that steamboat commerce should remain the Mississippi's primary transportation method. Political pressure mounted to abandon the project entirely and compensate steamboat operators for navigation disruptions caused by the useless stone piers. Yet Eads refused to accept defeat or modify his revolutionary design principles. While critics celebrated the apparent vindication of European engineering superiority, he studied the measurement discrepancies with characteristic obsession. The 2.5-inch error reflected thermal expansion calculations that had proven slightly inaccurate across the massive scale of the bridge spans, but the chrome steel itself had performed exactly as specified. The problem lay not in the materials or construction methods, but in the unprecedented precision required by tubular arch design. Working with Chauvenet and Flad, Eads developed a solution that would have been impossible with traditional bridge materials. Instead of scrapping the expensive chrome steel components, he proposed cutting the oversized tubes in half and rejoining them with custom couplings that would eliminate the excess length while maintaining structural integrity. The approach demanded metallurgical techniques that had never been attempted on such massive structural components, requiring specialized equipment and welding methods that pushed American industrial capabilities to their limits. The coupling solution represented a fundamental breakthrough in steel fabrication technology. Chrome Steel Company engineers worked with Eads to develop joining techniques that would create connections stronger than the original continuous tubes, using precisely machined sleeves and advanced welding methods. The process required heating massive steel components to exact temperatures while maintaining dimensional accuracy that allowed perfect alignment when the pieces cooled and contracted. Critics dismissed the coupling approach as desperate improvisation that would create weak points destined to fail under load. European engineering theory suggested that joined steel components could never match the strength of continuous pieces, predicting catastrophic failure once railroad traffic began crossing the bridge. The established wisdom held that structural integrity demanded uninterrupted materials, making Eads's proposed solution a dangerous gamble that would likely collapse within months of completion. The financial pressure intensified as coupling work required additional months of delay and hundreds of thousands of dollars in specialized equipment. Investors who had survived the initial crisis now faced extended uncertainty about whether the modified design would actually work under real-world conditions. The bridge company's creditors demanded guarantees that Eads could not provide, since no similar coupling techniques had ever been tested on structural components approaching this scale. Construction resumed in late 1874 as Chrome Steel Company delivered the custom couplings and specialized welding equipment necessary to complete the arch closures. Each coupling required precise machining and assembly techniques that transformed the bridge construction site into an advanced metallurgical laboratory. The process demanded temperature control and dimensional accuracy that exceeded anything previously attempted in American heavy construction, pushing the project's total costs toward levels that threatened the financial viability of future bridge projects. The success or failure of Eads's coupling solution would determine not only the bridge's completion, but the future credibility of American engineering innovation. European observers waited for the predicted catastrophic failure that would prove experimental. American methods could not replace proven European techniques. Carnegie and traditional steel manufacturers prepared to capitalize on Eads's failure by positioning mass production methods as the only reliable approach to major construction projects. Yet, as the coupled steel components moved into final position during the winter months of 1874, the chrome steel demonstrated exactly the performance characteristics that had justified Eads's enormous investment in experimental materials. The joined tubes aligned perfectly, creating structural connections that exceeded the strength specifications of continuous components, while proving that American precision manufacturing could solve problems that European theory declared impossible to overcome. The most unconventional test in engineering history began on June 14, 1874, when a traveling circus elephant named Bolivar became the first living creature to cross the completed Eads Bridge. Popular folklore held that elephants possess supernatural instincts about structural safety, refusing to walk across bridges that might collapse under their weight. As Bolivar's massive feet touched the chrome steel deck and began the 520-foot journey across the Mississippi, half of St. Louis gathered along the riverbanks to witness what they believed would be the ultimate validation of American engineering. The elephant test reflected both scientific curiosity and practical necessity. Eads needed to demonstrate his bridge's safety to a public that had watched 3 years of experimental construction with growing skepticism. Traditional load testing used static weights that could not replicate the dynamic stresses created by moving traffic, but living creatures provided unpredictable movement patterns that would reveal any structural weaknesses. Bolivar's deliberate pace across the span created constantly shifting load distributions that tested the chrome steel arches under conditions no mathematical calculation could fully predict. Crowds cheered as the elephant completed his crossing without incident, but Eads demanded more rigorous proof of his bridge's capabilities. On July 2, 1874, he orchestrated the most demanding structural test ever attempted in American construction. 14 locomotives, each loaded with 30 tons of coal and water, would cross the bridge simultaneously. The combined weight of 420 tons represented 3 times the normal traffic capacity that railroad companies expected bridges to handle, creating concentrated loads that would reveal any hidden weaknesses in the chrome steel structure. The locomotive test required precise coordination between multiple railroad crews and careful positioning to maximize stress on the bridge spans. Each engine weighed approximately 30 tons empty, and the additional coal and water loads brought each locomotive to 60 tons of concentrated weight. Positioning 14 such engines across the bridge's 3 arches created load distributions that pushed Eads' structural calculations to their absolute limits, while providing visual proof of the bridge's strength that no skeptic could dismiss. Engineering observers from across America gathered to witness the test, many expecting to see the collapse that would vindicate European warnings about experimental American construction methods. Carnegie's representatives attended with particular interest, hoping to document the failure of precision manufacturing approaches that threatened mass production dominance of the steel industry. European publications had sent correspondents to record what they anticipated would be the spectacular failure of American engineering arrogance. As the 14 locomotives moved slowly across the spans, precise measurements revealed deflections within calculated limits, despite the enormous concentrated loads. The chrome steel arches absorbed the weight without the catastrophic failures that European theory predicted for experimental materials under such extreme testing conditions. Chauvenet's mathematical calculations proved accurate, as the bridge demonstrated exactly the load-bearing characteristics that his equations had predicted, validating American empirical testing methods over European theoretical approaches. The successful locomotive test created international recognition of American engineering superiority that extended far beyond bridge construction. European publications grudgingly acknowledged that Eads' combination of experimental materials, precision manufacturing, and innovative construction methods had produced results that surpassed anything achieved through traditional approaches. The chrome steel's performance under extreme loads demonstrated material characteristics that European foundries could not match using conventional carbon steel production techniques. July 4th, 1874, marked the bridge's official opening with ceremonies that celebrated both St. Louis's commercial future and American engineering achievement. President Ulysses S. Grant attended the dedication ceremonies, while General William Tecumseh Sherman drove a golden spike to commemorate the completion of the railroad connection that would transform St. Louis from a river port into a transcontinental transportation hub. The festivities attracted over 500,000 spectators, who witnessed 15 miles of parades celebrating the triumph of American innovation over European skepticism. The opening day celebration vindicated every controversial decision Eads had made throughout the 7-year construction process. Chrome Steel Company's expensive experimental alloy had proven its worth under the most demanding test conditions, while individual component testing had eliminated the material failures that plagued conventional construction projects. The cantilever construction method had delivered precision that exceeded traditional building approaches, while keeping the Mississippi's shipping lanes open throughout the construction period. European engineering publications published detailed technical analyses, acknowledging American achievements in materials science and construction methodology. The bridge's successful completion under extreme test conditions forced a fundamental reassessment of international engineering capabilities, with American methods gaining respect that had previously been reserved for European approaches. The chrome steel's superior performance characteristics challenged European assumptions about metallurgical science and manufacturing techniques. The long-term implications of Eads's success extended beyond immediate engineering recognition to fundamental changes in American industrial development. The bridge's completion proved that precision manufacturing and individual component testing could deliver results superior to mass production methods, encouraging other American engineers to pursue experimental approaches rather than copying European techniques. The chrome steel's durability characteristics suggested that American materials science could exceed European standards through empirical testing rather than theoretical calculations. Yet the most remarkable vindication of Eads's revolutionary approach would emerge over the following decades as the bridge's chrome steel demonstrated longevity that surpassed every prediction. While conventional bridges required regular replacement of structural components worn out by weather and traffic loads, the Eads Bridge maintained its original chrome steel elements without significant deterioration. The experimental alloy that had cost enormous amounts to develop and test proved more durable than the galvanized carbon steel that became the industry standard in subsequent decades. Modern engineering analysis would eventually reveal the fundamental superiority of Eads's chrome steel over contemporary materials. Testing conducted in 1988 demonstrated that the original chrome steel retained structural characteristics superior to modern galvanized beams despite inadequate chromium content by current metallurgical standards. The irony became apparent as 20th century bridges required replacement every 75 years, while Eads's 1874 experimental structure remained functionally unchanged after more than a century of continuous service, proving that American precision manufacturing had achieved results that mass production methods could not match.